Sure. What is the effective temperature on equilibrium according to Le Chatelier's principle? Okay, this was part of the homework. This was something that a couple people wrote as a muddiest point. So let's go ahead and just very rapidly. We have the formation of water, right, from its constituents. In your homework, I think you do receive this reaction somewhere, or maybe last time we calculated it and it was about 480 something. Right? Pay attention to whether you're in per mole or whether you've actually just been given kilojoules for the number of mole equivalents you've actually calculated. Okay. What type of reaction is this using the terminology from the first slide? Exothermic, perfect, okay? So when you're asked by Le Chatelier's principle, if you put in temperature, if you raise the temperature by putting in heat, which direction does this want to go? Okay, it wants to go to the left. Why?
Just the side that absorbs more heat.
The side that, explain that again, sorry.
Wait.
Where is heat on this reaction? If I wanted to draw it like one of the reacting species. I would put it over here. Kind of like when I drew ATP earlier and I said like, ooh, energy comes out, right? Same thing with this. For our exothermic reaction, heat is like a product, basically. We know that when this reacts, we'll release heat. That is the definition of the exothermic. So if I put in heat for the purpose of raising the temperature, it's like I've put in a product. And Le Chatelier says when you change the concentration of one of your products or reactants, you want to go back the other way to reach equilibrium. So you can think about it as you put in heat, you'll want to go back this way towards products. Okay? You need this piece to answer that question though. If you aren't told the enthalpic change of your reaction, and I just say like you've put in temperature, what happens? You could say I cannot tell you that until you tell me whether this reaction is exothermic or endothermic. Okay. What's the effective temperature on the equilibrium constant? Does it matter? Do you think it matters? I think I heard someone saying, mm-hmm. The answer is that it does. Don't worry, I haven't told you how it matters yet. You're not expected to know. Equilibrium constant is a bit of a misnomer because it's only constant when you're at a constant T. Once you change T, Keq changes. Okay. Standard state free energy change can be given by negative RT, the natural log of Keq. It can also be given by standard state change in enthalpy minus T times the change in S. Remember that this is only for Keq. If you're not at equilibrium, otherwise you have our reaction free energy equation. We have this piece plus our Q piece. Okay? So what you can do is we'll take these pieces here, okay, and we're going to rearrange them. We're going to leave natural log of Keq by itself and move gas constant and temperature to the other side. Over R, okay? I moved RT over, this T dropped out over here. So this looks kind of like a linear equation. What's the X? 1 over T, great. This is called the Van't Hoff equation, this piece here. And basically what it says is it's describing a linear relationship between natural log of equilibrium constant and 1 over T. There's a linear relationship that exists between natural log of Keq and inverse absolute temperature 1 over T. So you can plot it. put 1 over t here. Natural log of Keq on the y-axis. And it's gonna look like this. What's your intercept equal to? Delta S over R. Change in entropy at standard state over the gas constant is my intercept. My slope is negative change in enthalpy at standard state over R. I said Keq is measurable. The concentrations are measurable. We could use some type of spectroscopy measurement to figure this out. Temperature is obviously measurable. That's nice and easy for us. So one thing you could do with this relationship is vary temperature, measure changes in equilibrium constant, and get out for yourself change in entropy and change in enthalpy, okay, off of this plot. One of the things this does is it does assume that changes in entropy and enthalpy are temperature independent, okay? Because this slope is not changing, neither is this intercept, and we are changing, we're varying temperature. It's an assumption that works, okay? Over the ranges we're gonna talk about, it'll work. So again, you could use experimental values in the plot to back calculate for yourself H and S. Let's look at this, let's look at a drawing that I didn't make. And let's answer another question. Okay. This is from last